Ladies and gentlemen, a very warm welcome from our side to this Contact Mechanics Conference here in Delft. It is our very special pleasure and our honor to be here keynote speakers. What can you expect today out of our keynote? Well, we'll give you an introduction and do a rail reprofiling review. Looking at presently discussed rail reprofiling issues, and we will especially focus on squats and studs. Give you a conclusion and a rail reprofiling outlook. And we will do this from a rail grinding perspective and from a rail milling perspective. A quick review about my history and contact mechanics. I started in 2003 as a passive attendant. I was co-author there at the paper. And from 2006 onward, I regularly presented on the topics of wear, RCF, rail grades, and friction management.
And also from my side, a warm welcome. And the list of my participations is not much longer, but it dates back early. My first participation was in Cambridge in 1990. And from 2000 onwards also I had the pleasure to present each time a paper, and I was very honored when I got the invitation to speak as a keynote speaker here. Well, talking about history, let's also look a bit back in the grinding practice where I'm coming from. 1981, the real year when I came in contact with the first grinding machine in Munich underground in Germany, where I had the duty from the railway side to organize the very first demonstration campaign, where I got the Speno and the grinding virus, which you can't get rid of if you have it. Well, since that time, grinding had quite a big development. Originally had a fairly low productivity rate, and I would like to mention already in this moment that grinding has always been known to produce traces of martensite, which are reduced or removed by the traffic, and we will come back to that at the end of the presentation again. Well, there was of course a demand for more effective high production grinding, and therefore also for more aggressive one, which was standard with heavy haul railways, whereas in Europe there was and is still some resistance to accept a more aggressive style, and probably for good reasons. Well, it's not just grinding.
So there were also some other developments taking place at the same time: an increase in axle loads, more traffic speed, increased train frequencies, higher traction power, slip-controlled locomotive, and all in all, less time for rail maintenance. So this led to the development of rail milling. There was a demand for increased metal removal capability, remove deep defect, restore the rail profile, and also produce a surface quality with respect to specific acoustic requirements. And of course, have a technology at hand that can address these deep defects as well as also low metal removal rates.
Specifications for rail grinding are fixed in a European norm, 13231, which is talking about reprofiling of rails, because the definition and the specifications, of course, should be independent of the used technology, and therefore we try as much as we can to use that term throughout this presentation. The development of rail reprofiling had some quite remarkable effects. Today, gauge corner fatigue is basically under control, also thanks to the anti-hedgehog profiles, and today we are aiming at one-pass or two-pass grinding, low metal removal rates taken away in cyclic programmed activities. There's a question whether there shouldn't be different specifications for different applications of railways, for instance, high rail, heavy haul rail, high speed, or conventional or urban traffic systems. And there is also a little bit of debate whether the specifications should be aim more at high production, the quantity, or should aim more at the surface condition issues, which deals with the quality, but probably reduces a little bit the quantity. For good reasons, because today we are talking about different rolling contact fatigue phenomena, and also this presentation in the introduction should not so much answer the problems, but point the fingers to the problems we should discuss and we should find then solution for. Already some maybe a little bit provocative remarks. The planning is usually based on the theory, which means we aim at removing or reducing surface defects by constantly providing optimal contact conditions. Easy said, not so easy done. Intervention cycles used are from as little as 15 million gross tons to as much as 150 million gross tons, and the respective metal removal rates from 0.1 to 0.3 or even more metal removal per intervention. Everyone is aiming at optimized reprofiling programs, one pass and you leave the site and you go to the next one, and that should keep the rails always in good condition. But all these one pass action and do it every time the same is based on, of course, overall constant conditions. But we have different track conditions, different traffic and operational conditions, and also, or as a consequence, different defect types and development. So which means a one-fits-all policy is maybe not the best one. Richard will explain in detail a little bit how that works.
So we kind of have now an idea what we want to do. Let's now look at some implementation strategies, how to achieve this. And what you can see here is a diagram that shows the RCF damage classes on the y-axis, good, light, medium, severe, and the tonnage. And this was, by the way, taken from ProRail, and we applied some modifications to this. So when a rail is installed, it takes some time until damage will develop. First slow, then faster and faster, cracks will grow deeper, and at some point a safety limit is reached, and then the rails will be removed, a new rail will be installed, and the whole cycle continues. Okay. You can imagine that this is not a very economic strategy for this. Let's look at an ideal program now. Starting with an initial reprofiling to get rid of all defects that might be there on the rail to produce a high-quality rail surface. Again, the whole story starts, damage starts to develop, but now we do cyclic preventive reprofiling with low metal removal rates in order to keep the rail surface in this good condition, in this low to no damage condition, thereby extend the rail life and thereby providing, of course, a solution with a high economic benefit. Reality is sometimes different, and reality often diverges from the optimum solution. So sometimes we cannot do the initial reprofiling, so damage starts to grow, and for what reason ever, we come back later when we already have some damage, so some corrective maintenance might be required, or even some restorative maintenance if the cracks are really deep. Nevertheless, when this is done, we of course then can implement a preventive cyclic strategy and keep the rail in the optimum condition. Another example, we miss one of the cycles. So everything starts really great. Initial reprofiling, the cyclic preventive maintenance, but then this cycle is missed. So if we would just continue with this cyclic preventive strategy, we do a little bit of reprofiling, but not enough to keep up, and soon the damage would get out of control and we would need to exchange this rail. However, now we need to adapt. We need to implement a corrective cycle, we need to implement a restorative cycle, get the rail back into the condition we want to have, and then continue with the cyclic preventive strategy.
So, this missed cycle is something which happens pretty often. If you look at the daily reports, it very often states we could start grinding 20 minutes late, there was no work window there, or we had to finish earlier, or there was even no access, the shift has been cancelled because a pilot didn't show up, or it has been reported that sometimes a machine may have a breakdown and can't do the work, which means at the next day, particularly when you do one-pass grinding, you can't go back to where you have been. Or the other question is, we are asked, well, do as much as you can and leave the site, the grinding or the reprofiling site, halfway treated. And what may happen is that these defects, which have been there and which are still partly there, may change their development. For instance, on the surface, the crack doesn't start at the gauge corner anymore. As it is reduced a bit down, it starts more to the center of the rail. Or there is a risk, or could be a risk, that from this remaining crack, even if it's a small one, some other things like squats or studs, as we will hear in a moment, can form, or spalls fall out of the rail surface. And that, if it happens on these places where grinding, cyclical grinding has been missed once or another time, locally, more severe defects may occur, and when they are there and bigger as expected, this is because some time ago something may have happened. So that may explain some of these unexpected defects. So in short, partially treated defects, whether it's during initial or preventive grinding, may develop differently, and there is the need for more metal removal afterwards. Corrective interventions triggered or controlled by measurements when they have been made and are available. I like this picture, or these two pictures, which I have seen the first time at the Heavy Haul Conference in 2015 in Perth, thanks to Stuart Grassi, who presented them in a paper, where you see all the things which we hopefully will discuss in these days: head checks, wide edging layer, martensite, squats, studs, and also roughness issues of the surface. Now all this goes somehow together and leads sometimes to surprises. It was here in Delft 5 years ago when this picture came up on the screen and was discussed. Oh, grinding, aggressive grinding has resulted in this effect in the spall in the center of the rail. But if you look at it, you think, well, in there it's pretty rusty and pretty old surface, so it probably can't be the grinding just a few weeks back. With the many pictures I have taken in my pretty long career, I found this one from 1988, made in, I guess it was in Sweden, at that time a fairly low productive grinder. The train chief made 8 passes, took this photograph, sent it, not by email at that time, of course, it took some time, and asked, what should I do before grinding? The surface looked pretty nice, and when I started grinding, all of a sudden I had this one. There was something, something underneath in the railhead, which just became apparent by grinding. And 1 year later, in 1989, I made that picture in Brazil on a heavy haul ore line, where we started with a small 16-stone grinder to show them what beautiful things a rail maintenance can do. We made a few grinding passes, had to leave the site, and our ore train was passing, and when we came back, that piece has spalled out from the gauge corner. Oh, as a young engineer, remember 89, what should I do? You look at it, and after a while you say, well, that's a fresh broken rail, but around is a rusty surface which comes from a crack which has been there for quite some time. So grinding didn't provoke, well, it provoked the spalling, but it didn't provoke the damage inside the rail. It just made it apparent. Bearing this in mind, I would like to hammer the nail a bit further down, not in the rail maybe, in wood. So this is a transversal cut of apparently heavily head-checked rail on the gauge corner, made in Germany on a lab. And the overall depth of the defect is about 3 millimeters. If we start now grinding, reprofiling, we take off 1 millimeter, and that's the situation. So look, where the head checks, the crack started before the action, is no more the crack. Now it has shifted, the origin of the crack on the surface shifted towards the center of the rail. So we would take off more with reprofiling, and now all the defects, the big defects, are gone. But close to the center, there are 3 cracks which are there, and we will learn later on that maybe that may trigger another defect. If we had taken away everything, at least there would be no stress razor, no initiation point, even if the metal underneath has already suffered from quite repeated loadings. And once again, on that nail, seen from in the longitudinal profile, remarkable cracks there, we do our best, program a rail reprofiling interaction, time from 1 millimeter to remove, and we see, well, a little bit of the surface looks better. We grind more, and we see some crack goes more horizontally, the one on the left-hand side, almost parallel to the surface. The one in the middle has already turned towards the rail foot. So now you can imagine, after such a partial removal of defects, these defects will grow differently than before. Plus the effect that the contact conditions between the wheel and the rail from the transverse profile is different. And even if we do more, there is still one stress razor left at the surface of the rail. So this is a crack which is there directly after the intervention. Which means, once again, we should probably not just think preventive, taking our medicine every so often cures the problem.
So after seeing a few examples of different defects, especially squats, let's have a little bit of a look back in history on these defects. So squats were observed in the 1950s in Japanese railways called dark spots at that time, in France and the UK in the 1970s, 1980s, and then we saw a reappearance of this defect in the late 1990s. So a typical squat from the 70s and 80s, heavily sheared rail surface, correct initiation and growth by ratcheting, so an RCF-driven defect. Initiation after 10, 20, 30 mgd, and then growth over 100 mgd or even more until you have the full defect size. Straight track, shallow curves can result in rail breaks, and a solution was found by the introduction by preventive cyclic rail maintenance and also the introduction of RCF-resistant rail grades at this time. Mid-1990s, this defect seemed to have reappeared. This defect that has superficial similarity to these classic squats, mostly epidemic appearance, formation out of the blue. Within 10 mgds, you can have a full-grown defect already. There was not much plastic deformation found on the rail surface. Massive spalling was possible, as Wolfgang has reported, but no direct rail breaks so far were associated to this defect, and conventional cyclic rail maintenance strategies seem to have been of limited mitigation success. So there are differences between a classic squat and a new squat, so perhaps a new name might be necessary for this defect. Because almost all of the squats we see today can be characterized as new squats. And different names have been developed. Well, squats are still used a lot for this defect because it looks very similar. Everyone is used to this. But also squat-type defect, squat-like defect, stat, new squat. Well, we decided to use the name stat because we want to highlight this is something different, and of course, it's a very short and crisp name. What do we need for a stat? So we need an initiation point. Local profile deviation, local track geometry deviation, weld, RCF, imprints, head checks, wide edging layers. Very important, we need to have high stress contact condition. A narrow contact patch on top of the rail will favor the formation of a stat. And studs are also found mainly in low wear environments. So low wear can be caused by a wear-resistant rail grade or by low tonnage contact conditions. So a low wear environment will keep these high stress contact conditions on top of the rail active over a longer time and will give the opportunity for a defect to develop and grow. Something else very interesting happened roughly around the same time, Wolfgang mentioned it, the introduction of so-called anti-head check profiles to keep head checks under control. So some slight gauge corner undercutting to shift the contact towards the top of the rail, to create a top of the rail concentrated contact. So the question is, do anti-head check profiles perhaps favor squats and studs? Traction conditions, studs are found in high traction areas, signals or stations or general acceleration sites. We have seen the continuously increase of train frequencies, traction power, the move from DC to AC traction allowing controlled operations at higher slip rate with higher tractive power, distributed power, so this means more axles, driven axles by train, and also a little bit of a question mark still, changing friction conditions, what might this do with respect to this defect? System stiffness. Empirical evidence was found that studs will tend to grow in more stiffer systems, either stiff vehicle suspension or stiff track constructions. Nevertheless, this will increase the dynamic forces on a system. We've also seen an increase in rotational bogie stiffness to increase performance of passenger trains at high speeds. However, during curving, this will increase lateral forces and lateral creep. This point is really still a little bit difficult to quantify. So there are many theories out there with respect to squats and stud formation. I have chosen the so-called squat damage staircase concept, modified it slightly to the stud damage staircase concept, but this shows really how complex this is. We need an initiation point. We need to have the high stress contact condition due to the unfavorable profiles, low wear conditions, high traction forces, stiff rail wheel systems. So all these steps will add up, and at some point we are above a certain threshold, and squats and studs will start to form and grow.
So back to squats, because this was named in the literature. I found recently this paper in the Internal Journal of Fatigue from Chinese authors and Celie Lee co-authored and Rolf Dollywood. I don't make much publicity for this paper, but I was looking into the figure, a few figures just like to share with you and to trigger some discussion afterwards. The figure 5 shows a squat has been found. They started the project in 2007, and it was made clear that this rail has never been ground or maintained, reprofiled before, and it was monitored in the course of the years, twice a year, so you can quite clearly see the defect grows and cracks start in the middle to form. And then it happened sometimes in 2010 in June that a grinding train ran over for whatever reason someone has programmed. They found afterwards out 1 millimeter has been taken off. And what you can see is the squat is still there. No wonder, we have seen just before why. What you also can see is the contact band runs right over that squat, so concentrates now the loading up there. And you can also see a very aggressive surface has been ground, but the problem was before there, so it was not created by this action. And then we look at another picture, which also makes apparent why it is so important to go to the roots and to eradicate everything. In this row, you see different squat types, smaller one on the left-hand side, always more severe towards the right side. Also interestingly described how the cracks are there, and the middle ridge forming, and the Y-shape and U-shaped cracks. And compared to that, after this unintentional grinding, what has happened? Well, the smaller squats disappeared. No cracks could be detected when measuring afterwards. The bigger squats, they can be clearly seen, and also the U-shaped crack, a U-shaped crack has been found when examining. And the biggest one, well, you have already seen such a picture. Well, it is there, pretty aggressive grinding, and one can discuss whether this has a certain effect to what happens next, but interesting to see what happened before. And on this particular squat and partial metal removal of 1 millimeter, it happened that not only it has been ground once halfway correctively, it has also been ground 2 years later, 2012, with at that time programmed cyclical preventive pass. Good reason, you know, we make once a year a 0.3 millimeter metal removal, but the squat, which has been there before, remained after this 0.3 millimeter metal removal, and you look just at the traces of a longitudinal profile or transverse profile recording the good work the machine has done, that squat doesn't become apparent. They say, well, I'm still there, and therefore they had to change the rails as they were monitoring this. So I think it is quite clear that it's a very complex matter.
So after having seen this, what is now the contribution that rail maintenance, rail reprofiling can do with respect to studs and squats? Well, when looking again at this staircase concept, we can see that rail maintenance can address at least 3 steps to provide some mitigation. So, initiation points, rail maintenance, if applied correctly, can remove the initiation points and preferably should not introduce any new initiation points. With rail maintenance, we can adjust the profile shapes to provide low-stress contact conditions. And of course, if there are already existing deep defects, rail maintenance will introduce the right amount of wear to remove these defects. A few remarks. First of all, in order to do this, we need to have time for reprofiling. We have seen increased traffic, 24/7 operations, maintenance windows becoming shorter and shorter, faster and faster damage growth. So rail maintenance, rail reprofiling is required to achieve more in less time, to be more aggressive, remove deeper defects more efficiently. And now all of a sudden we come into an area where side effects and limitations of specific technologies might be an issue and need to be considered. Selection of technology. We talk about rail grinding with rotating stone. We talk about rail milling with rotary cutting tools. There are different selection criteria, technical specification and scope of work. How much track can be finished within a certain time period? Do we need preventive, corrective, or restorative maintenance to apply at a specific location? Economic considerations, and of course, is the specific technology available for this specific network or not? Measurement. We need to quantify, we need to characterize the damage. We need to know the dimensions of the damage, and we need to do these measurements periodic so that we can develop some kind of damage progression, that we get an understanding how this defect progresses. And you could do it just visually, as Wolfgang has shown in his slides. Looking at this, taking some measurements, you can use ultrasound, you can use electromagnetic technologies. Nevertheless, this will tell us when to come in and do reprofiling, and of course, how much metal to remove to get rid of the defects. And very importantly, also these technologies shall be on the reprofiling train, because you want to prove after the train has gone through that we achieved what we were supposed to do. We want to introduce artificial wear to completely remove the damage. A restorative approach for really deep defects, a cyclic preventive approach for shallow defects. We have seen that remaining defects on the rail surface will always act as a crack starter, even as a crack accelerator. So we need to make sure we introduce the right amount of wear to remove the cracks, but not more, not more. We want to precisely produce the desired target profile to avoid high-stress contact conditions. But the big question is, with respect to these defects, what is the right target profile? It seems like so far we have only produced SF profiles, SF as in squat fertilization. Profile quality, well, we want to remove all defects and initiation points, and also the longitudinal profile shall be accurate with respect to short and medium wavelength, as well as micro roughness.
And just to add a comment, a too small contact on a very perfect profile, which is run over by very perfect wheels, is maybe concentrating on a spot, and one should also consider to maybe spread that wider, so the profile issue is still there. Coming back to the surface, and I have already made at the beginning this remark about the martensite by grinding, which may be one part of the story, but it's much more complex. First of all, no initiation point for new defects should be left after the reprofiling, and what needs to be considered and discussed is the roughness, which could be rougher for heavy haul and probably should be finer for light axle load traffic in urban areas. We could discuss about faceting, which once again is the question of the finishing pass at the end. If it's the grinding technology, you can have every surface quality if you just request the right one. The question is about coloring, indicating temperature changes on the surface, and of course the martensite. So all this may play a role, but not the only one. And I think with this, we come to the remarks and end situation. What should we discuss? Do we need different specifications for different traffic types? Heavy haul, mixed traffic, light axle loads? Could we concentrate on those cases and those locations where we have a growing appearance of rolling contact fatigue? Because there are some particular hotspots, and the question is, why is there a problem and why is it not on other places? And we should also debate, well, cyclic grinding is a good thing, but to call it cyclic preventive could be on one side too much metal removal, not allowing any small defect coming up, or could we allow some small defects, but we then have to take care that we can reduce it completely, and therefore we need measurement systems on our reprofiling machines. In summary, 8 minutes left, we don't need all these 8 minutes. Strategic rail profiling is a cyclic action. You can't do it once and forget. Preventive reprofiling and locally corrective work, I think we can say they go together. Continuous recording, documentation, and use of that documentation is important to be able to adapt the strategy and not to react when we see already, oh, something has happened we don't like. Partial crack removal may mask, maybe not everywhere, but may mask deeper damages and therefore result in accelerated damage growth if it's not monitored correctly. So, 3 things: detailed planning, precise preparation, and adapted execution. And mind detailed planning allow for some delay of reprofiling work, which will usually not be taken up the following day or not even in the next intervention campaign to say, well, we missed that spot last year, so we have to do at least double that much metal removal. Timing, availability, and production capabilities are really important. In summary, rail reprofiling, whether it be grinding, milling, or whatever, is a proven method to control rolling contact fatigue when adapted correctly and according to adequate specifications. Undesired side effects may be considered, as everyone who goes to a doctor because he feels sick or ill knows when he gets something, treatment, medicine, there is said you take 1 pill every day or 1 in the morning and 1 in the evening. But if you take too much, because better could be useful, you may even feel worse after the treatment. And therefore, as we have only vague information in our prescriptions for the cyclic reprofiling, more research and an open collaboration of everyone, every party involved is required. So, coming back to my favorite analogy, don't challenge the medicine, use just the right dose. But the question is, what is the right dose? Or, coming back to the title, please read the user guide. And if it doesn't work to your condition, maybe you yourself can adjust it. And maybe there is none. Nothing has been delivered when you bought that rail, how it should be reprofiled, then you have to establish one. So with this, I come to our last slide. Wheel-rail contact is complex. Yes, and therefore we should come together and study it. And not only the researchers, also those using these technologies should be probably more involved in this. Rails need to be studied in track. It is good to have the modeling. It is good to make all these fantastic virtual reality things. But I still believe that being in track and looking to the rails is the best way to get an understanding what it is. Now, whether you are kneeling in front of the rail, as Richard on the right-hand side of the picture, or if you are enjoying, other ones were doing the work for you and considering, well, what could we do or what could we do better? Anyway, every one of us likes the job. Sometimes it's a great one. sometimes it's a question mark behind. With that, we thank you both for your attention and are looking forward to the respective discussions.
Thank you.